Hey, it's day 81 chemistry, and it's a good chance for us to take a look at the idea of equivalence point, using that to figure out the difference between strong and weak acids and where that equivalence point would actually fall. And then we're going to do the important thing. We're going to combine stoichiometry with titrations, with Stoich and titrations, baby. You can never get tired of the Stoich. It's just so easy. Cool. So if we look at this, of course, you'd normally be turning in some ETDs, but we won't worry about that today. Look at that little bugger. Get out your notes. I know notes don't get you excited, but that little smile does, right? So key things that we need to know first, when we combine stoichiometry, the changing of substances, with titration, looking for the neutralization of acids and bases, that's basically what we're doing. We're always going to have an acid-base reaction, at least in this class. And anytime you mix an acid with a base, you always make two things, salt and water. So like in our lab today, you can mix sodium hydroxide with hydrochloric, a strong base with a strong acid, and you'll make sodium chloride and water, HOH, right? So if we look at this, of course, anytime you titrate a strong acid, a great quarterback likes to throw the proton, right? With a strong base, a great receiver, then the equivalence point where the H and the OH match up would be 7, a pH of 7, because you got a great thrower and a great catcher, right? Good quarterback and a good receiver. This simply means that the piles of hydrogen ions will be equal to the piles of hydroxide ions. And if you put those together, then you get HOH, right? So that's why, of course, this is a neutralization when you do a titration. This, of course, depends on the mole-to-mole ratio. That's what always matters. And, of course, that's why you should always take a look at your reaction and make sure it's balanced. So you got the right mole-to-mole ratio. Now, there's a song about this. It's a beautiful one. Titrations, HOH. Titrations, HOH. I do miss my home of New York. All right. Now, key thing that we can see about this is you can see that I want you to solve two different problems. They have to do with neutralizing and have to do with mixing solutions. And, well, here's a reaction right here. Take a double look at it. So pause me, write down the questions, see if you can set up and solve them, because if you think about it, it's not that far off from the Stoich that we already did earlier in this year. Cool. Let's make the big ugly head disappear. Bye, a big ugly head. And we'll tackle this one together. So if we look at this, question number 1, or A, how many moles of sodium hydroxide are needed to neutralize 3 moles of sulfuric acid, right? Naming never goes away. First thing I should do is notice that I have a chemical equation, so I should check its balance, right? Always get in that habit. Now, if I look at this, I can see that I got a problem. There's 2 sodiums there, so I'm going to need 2 sodium hydroxides, and that's going to pump out twice as much water, right? Hey, now it's balanced. Now I can use it, right? Then it's saying how many moles of sodium hydroxide. That's what I need. So at the end of this, I better have moles of sodium hydroxide. That's my target, right? And I want to neutralize it with 3 moles of H2SO4 because, of course, it's got the H's in it. Well, okay, that's not too bad. That's the only number I got. I'm going to start with 3 moles of H2SO4, sulfuric acid, and I'm going to convert it to moles of the other thing. I could use the mole-to-mole ratio, right? So I'm going to go from moles of the thing I don't want, my acid, my H supplier, to moles of my base, my receiver, my sodium hydroxide with the OHs, right, the hydroxides. And if I look at my ratio, I can see it is a ratio of 1 of those for every 2 of those. That's because it's an H2, right? It's got 2 balls there, right? It's throwing out the protons twice. Now, when they do this, of course, it's some pretty easy math. You don't even need your calculator. It's 6 moles of sodium hydroxide. Hey, look at that. It's twice as much. Kind of makes sense. There's 2 of those for every 1 of those. Oh. So when I'm looking at what this means, that means that in my 6 moles of sodium hydroxide, it's not the sodium I care about. It's that it's got 6 piles of hydroxides, floating piles, right? And all those hydroxides that are in there, they need to be canceled out. And when they get canceled out, they get canceled out with my 3 moles of H2SO4. He is with strong acid, so he's quite a quarterback. He's what's called diprotic, which means he can throw out both of those footballs, which means that I can produce 2 protons for every sulfuric acid. And that means that, of course, I'm going to have in this, well, 2 times the 3, that's 6 piles of protons. Hey, 6 and 6. That would make a whole bunch of HOH. That would make 6 waters, Titration, HOH. In neutralization, you're always matching up the H's with the OH's to get to your equivalence points so that they equal each other, the H's to the OH's. It's almost so easy it hurts. Oh, it doesn't burn, though, because it's neutral. Now, if we look at the next part, of course, this is looking at a bit more complex, so it looks all scary. We double-check the balance. It's the same equation for the last one, so we need 2 of those for every 2 of those, right? Then you got to figure out what you got and what you need, and it gives you a lot of stuff. But what you need is you need the molarity of your sodium hydroxide, which means you need the base at the end of this. So that means I'm going to be going for molarity, which is, of course, moles over liters of sodium hydroxide. Cool. Now, usually if I need to know about my base, my OH, I start with my acid. And I know some things about this. I got a 30 milliliter sample of the base. I want to neutralize it, cancel every OH with an H. I got 175 milliliters of my acid, my H supplier, the sulfuric, and I got a pH, the power of hydrogen, to 1.8. That's a lot of stuff. Where do I start? Well, if I need to know about my OH, I'm going to go for my H, which means I need to know my hydrogen concentration, right? So I can find out something about my base's concentration. Well, that's fairly easy to do when we look at this because, of course, that means if I need the H, then I could use my P. I could use my P as a power. So 10 to the negative pH, which they're given to me, I can use that to find out the hydrogen ion concentration. They told me it's 10 to the negative 1.8, right? That's going to be the pH is 1.8. And so I use that as a negative power. And when I do that, it punches in and it gives me that 0.016 moles per liter of sulfuric acid. Hey, that's handy because that tells me the strength of the acid that I'm trying to, of course, neutralize the sample with. Oh, that's my H's, right? So what do I do with that? Well, I need to convert that to my base. So I could use stoichiometry. To do that, I would start off with my acid, my H's, right? My protons. And that's 0.016 moles in every 1 liter of this sulfuric acid stuff. So make sure that you stretch it out to moles per liter anytime you have the big M, right? Then I can ask myself, do I have a whole liter of this? No, I got 175 milliliters, which converts to 0.175 liters of the sulfuric. That'll get rid of the solvent and leave me with just the H's that I care about. Liters and liters cancels. Now I'm in moles of my H supplier. Then I don't want to be an acid. I want to turn it into base, so I'm going to use my old Stoich trick, the mole-to-mole ratio. It's not that tricky, right? I'm going to get rid of the sulfuric, the acid, and turn it into the hydroxides, the base, right? When I look at that ratio, just like the last one we did, it's a 1 to 2 ratio because it's 2 H's there for every 1 OH, right? Then the last step of that is that would kill off the moles of sulfuric. Now I got moles of base, but I need moles per liter. So that means I need liters on the bottom. And how much of this do I want to cancel out? Well, I want to cancel out 30 milliliters. That's equivalent to 0.030. Just jump the decimal 3 to the left, right? And of course, I don't put anything on top because it's just dividing by it. If it makes you feel better, you can put 1 sample for each of those, right? Just so you don't have it hanging there in empty space. Cool. If I look at this, that will leave me with moles of sodium hydroxide over liters. Hey, that's moles per liter. And I chug and plug it into my calculator. I got 2 siggy figgies to start off with because I got it from my pH, and all my least accurate have 2. And that means that I can apply it and say, hey, it's 0.19 moles per liter, or molar, sodium hydroxide. Now, before I box that up and submit it, I have to ask myself, does it make sense, right? Well, consider this, right? I got 0.1 molar sodium hydroxide, and the acid was a pH of 1.8. A pH of 1.8, that's really low. That's very, very low for pH. That's lots of protons, right? So this is a pretty strong acid. Makes sense, it's sulfuric, which means that I got this beaker, and it's got lots of protons in it, right? Lots of piles of hydrogen ions, and I got 175 milliliters of sulfuric. That's a lot, right? I'm going to try to, of course, neutralize this out with just 30 milliliters of my base. So that means that my base, well, it's going to have lots of hydroxides, which means it's going to have a higher concentration. This is only 0.016. This is like more than 10 times as much, right? Oh, that's because this is going to have a lot more. It's going to need lots more of those hydroxide ions inside of it to match up the piles of H and OH because you're just going to cancel it out. So this should be like 10 times the amount, and it is because, of course, the pH is pretty darn low. So it's a strong acid. There's lots of protons to cancel. Always think about the number of piles of hydrogens and hydroxides when you're going after those because, of course, that's what's making your HOH to neutralize it. Cool. We would normally look at lab 23 in the pH calcs. With lab 23, let's show this together. You would have produced curves like this with speedy titrations of weak and strong acids. You should be able to predict with each of these curves what combination you were making and what the equivalence point was. So if we look at them, we can see down here, we'll start with this one here. You can see that on that one, right, we got this stuff called, of course, we'll zoom up there. We got a weak acid. We can tell because, of course, it's starting at a pH that's closer to 7. It's in like the, 3-ish category to 4-ish category. And then what I did to it was I added a strong base. That strong base was sodium hydroxide. So I got a weak quarterback. He throws the proton and then grabs it back. And I got a really strong base, which can grab any proton that's available. And that means that when they reach their equivalence point, it's actually slightly basic because you've got not only this strong base, which is the sodium hydroxide, you have the conjugate base that the acid becomes, so he becomes the new receiver. So with extra receivers in there, it pushes the equivalence point up to a little bit of basic land. There's less protons around because they've all been gobbled up, right? If I look at the next one, you can see that right here, this orange one, hey, well, that's the same pH, so you can tell that's a weak acid, but this time I combine it with a weak base. You can tell because it doesn't go very, very high. It's below, it's in the category of under 9, so that's closer to 7, so that's your ammonia. And if I got a weak quarterback with a weak receiver, that means that any of the protons that go out will be gobbled up, but not many of them are going out. So that means that I'd end up with a pretty good match of about 7. A really bad quarterback, really bad receiver, you're not going to get a lot of protons floating around in solution, right? If I look at the next one, the red one, I can see that, whoa, I'm starting at a lot lower pH, and that means that that's got to be a strong acid. There's lots of protons at pH of like 2, and at the end, it ends very high, so that's a strong base. And when you put those together, I got a great quarterback that loves to throw the proton like hydrochloric. That's why it's in your tummy. And I got a strong base like drain cleaner, which likes to gobble it up and receive it. So every proton that's thrown out, and all of them are thrown out with hydrochloric, get gobbled up by it, so they balance each other out as 7. Hey, this almost makes sense. A strong with a strong comes to a 7, right? Then we can see here I'm starting off the same low pH with the green line. Well, that's got to be a strong acid because it's a low pH. And then I can see that I ended at a pH that was below 10, so that means that that's probably a weak base that I've paired it with. There we go. The strong acid is the hydrochloric thrown at every proton, and then the weak base is the ammonia. Now, being a weak base, it catches the proton, becomes ammonium, and then a weak base becomes a strong conjugate acid. So it throws the proton back out, which means there's more protons floating around in the watery solution. Hey, that's extra protons. That would push the pH down to acid land. So you can always look at the curves and know what your starting pHs are and what kind of solution you have. These are all acidic, right? They're below 7. And your bases and how strong they are, where they're positioned. And then if you mix a strong with a weak, it's going to, of course, favor that imbalance of it. A strong acid is going to throw out more protons, and a weak base is weak because its conjugate acid becomes the next quarterback. So it throws it out there. So a lot of story in these little tiny lines. And this is kind of a big deal if we consider things like the ocean. With the ocean, we've got a problem of a weak acid, carbonic acid, as that goes into the ocean, of course. It throws out those protons. It gobbles some of them up, which doesn't shift the pH very much, but it's the coral reefs, the calcium carbonate, that's working to neutralize that stuff. And that's why, unfortunately, the pH is dropping because they're trying to reach their equivalence point. But that's why a scientist would do a calculation like they did on the second ETD, where they'd go out and read a pH reading, figure out what the actual number of protons were in the ocean, and then calculate how many milliliters of base you'd need to titrate in it to neutralize the ocean and save it, or how fast the reef was destroying. Not that you would use this for anything in real life, just something we might have to do to save all of our food chains, right? Now, get out your notes. Oh boy, they're already out. When we look at this, of course, we're going to try this problem. Stoich and titrations is our ultimate goal. A little bit easier problem for you here today. There's the reaction. Pause me. See if you can figure it out, since it's hard to talk to a chem buddy these days in isolation time and quarantine time. And we'll try it together. So, as always, we see a chemical equation. We balance it, right? Is it balanced? Yep, it's nice and balanced. We can see that we wrote HOH a little bit funny because this is all about titrations, right? So it says, of course, determine the volume of a 0.1 solution. So we need to know the volume of this solution, right, of the sodium hydroxide with that concentration. And we need to titrate 50 milliliters of this concentration of the nitric. So I got a lot of things, but in the end of this, I need a volume of my sodium hydroxide, right? And it's with that solution that's 0.1. So where do I start? Well, if I need to know about my OH, I start with my H. I need to know about my base, I start with my acid, right? And some things I know about the acid. I got 50 milliliters of it, and I got this concentration. Well, which one of those has more information in it? It's It's the one with the moles hidden inside of it. So start with the molarity, right? So I'm going to start with my 0.2 moles in every liter, 1 liter of the nitric acid, HNO3, right? And I got to turn that into my base. Hey, this is a titration, right? So first step that I would do, I want to get rid of this liter thing because it's annoying, and realize that I don't have a full liter. I have 50 milliliters, which is equivalent to 0.50 liters of that nitric acid solution, right? Cool. That'll kill off the liters and tell me how many moles I have. Now I want to change from acid to base. So I'm going to use the old mole-to-mole trick, stoichiometry. It's so easy it hurts. I'm going to get rid of my nitric, my hydrogen producer. I'm going to go for my receiver, my hydroxide. And if we look at this ratio, it's, well, that's not diprotic. It's monoprotic. So that means that it's a 1-to-1 ratio. Hey, nice job. Notice this is a strong acid, and that's a strong base. So it's pretty easy football to figure out. Equivalence point of 7, right? pH is 7. Then, of course, the next thing I can see here is I want to get the liters of sodium hydroxide. I've now killed off moles of that. I'm stuck with moles on top. How do I do that? Well, I do the old flip trick. I want to kill off moles and turn it into liters of sodium hydroxide. And this told me that in a solution that I have, that it is a concentration of 0.1 moles in every 1 liter of that. So I did the old flip trick on the actual concentration. That kills off the moles. And now I'm stuck with liters of the substance that I need. And you don't need a calculator to do this math because it's pretty easy, right? So when we slam that stuff in, it comes out to be 0.1 liters of sodium hydroxide, right? Now this is the same as 100 milliliters of sodium hydroxide. Now why does that make sense? Well, think about this. You started off and you had 50 milliliters, right, of the nitric acid. And that nitric acid, if we keep it simple, it had 0.2 piles of the hydrogen ions that are in there. 2 little tiny piles, right? 2/10 of a pile. Now I want to cancel that out with this stuff called the sodium hydroxide. When I do that, I recognize that I've got, 0.1 molar. It's only got 1/10 of a pile in every, of course, 50 milliliters. So if I want to cancel out each of these piles of hydrogens with the hydroxides, well, then I'm going to need twice as much, right? Oh, so I'm going to need another double the amount, so that would equal 100 milliliters of the 0.1 molar to get enough H's to max up with my OH's. Oh, HOH. And that's what this is looking at. If we think about the simple part of that, if I have an acid that is twice as strong, or a base that's twice as strong, then I will need twice as much acid to neutralize that. And that's where Lab 24 comes in, where you're actually going to use a known concentration of a base to figure out the unknown concentration of an acid. And that's what the goal of titrations are to do. They're there to find the concentration of an acid. So as we go into that, what we're doing, of course, is with our practice, we've been doing titrations, getting at those equivalence points. The equivalence point will help you to figure out the actual concentration of your unknown acid. So for this Lab 24, which we normally do in class, you'd have a burette. That burette would have a base that we know the concentration of. It's a 0.1 molar sodium hydroxide solution. And what you're going to be doing, of course, is dropping it into your acid, which is an unknown, to solve how many H's are in here, which will tell you its concentration. When we're doing that, of course, you're not going to add the base constantly. You're going to do it in pH intervals so that it jumps up like this graph. Each partner will have a different job. But what you're doing, of course, is you're building it up. We'd only do one trial, and it's about only 10 milliliters of the hydrochloric. Your job would be to figure out, as you look at those jumps, you're looking for the most vertical change in the pH. That's where the pH has shifted the most, where you've gone from extra H's to extra OH's. It's hard to get it just right. That's why we have to do it this way to look where the biggest change is. Follow across, and that would give you, of course, its concentration. Now, good things about this is hydrochloric and sodium hydroxide. So if you think about the last lab we did, that's a strong quarterback and a strong receiver. So it should have an equivalence point of about 7, right? If you do things right. Now, when you do this, there are 7 questions you need to answer. The first one, of course, is the molarity of the sodium hydroxide you're dropping in. That's point 1. I'm giving it to you. Then you would, of course, add it in steps. The pH would go from acid land to basic land, and there would be a jump. When it jumped the greatest amount going from acid to base, in the middle of that is your equivalence point. So we need to know the volume of the sodium hydroxide just before the biggest jump and just after to figure out what the volume is in the middle of that. So you take the average of those things. Then once you know how much sodium hydroxide you put it in volume, in milliliters, you can convert that easily using dimensional analysis to how many, of course, moles of sodium hydroxide there are. And since this is a strong and a strong, well, it's a 1-to-1 ratio if you write it out. So it'd be the same number of moles of the hydrochloric. And you know how many liters you put in, which was 10 milliliters in the beginning. So you take the moles divided by the 10 milliliters and, well, turn it into liters, and then you find out its concentration. It's that easy, right? Now, that, of course, would be your job to go into this and figure out the concentration of the unknown in a regular class. The secret to doing that, of course, is the base. Now, I'm all about that base, hydroxide. I'm all about that base, titration. When you need a solution neutralized, don't get the base into your eyes. It's really about the pile size. Because I'm all about that base, receivers. I know, it's pretty bad. Pretty basic, actually. Titrations. HOH. Our goal today was to be able to figure out where the equivalence point would sit with strong and weak acids. If you put a strong quarterback with a weak receiver, a weak base, then it's going to favor a pH that's less than 7, because not only is the quarterback, the acid, throwing out protons, but the weak base becomes a strong conjugate acid, which then throws out more protons. So there's extra protons fumbled around inside the solution, right? If you got a strong with a strong, it'll come out at 7. If you got a weak with a strong base, then it will be, of course, favoring the more basic solution. How do we combine Stoich with titrations? Well, the thing that we should notice is anytime that you have and you're starting with, it wants you to know about the base, then you start with the acid. If you want to know about the acid, then you start with the base, because it's all about titrations. HOH. Too bad my ugly face wasn't right there for that song.